Okay, so I do apologise for that interruption. So we were in the process of trying to decide what the PMF for the multinomial distribution was, where the vector little x1, little x2, little xk satisfies the conditions that all the components are elements of this set 0, 1, 2 up to k, and they all add up to give overall n. Okay, so the way we're going to do this is by considering it from the ball's point of view. So we throw n balls, and each of the balls can go into one of the k baskets. So basically what we're going to do is we're going to we're going to make a new probability space, which is the probability space containing absolutely every single outcome from the ball's perspective now, i.e. absolutely every single combination like this. So the first ball can go into 1 to k, the second ball can go into 1 to k, the third ball can go into 1 to k. So this element would be in this sample space. So all possibilities like that. Another possibility would be, let's say that a ball, the first ball goes into the kth basket, the second ball goes into the kth basket, third ball goes into the second basket, 1, 1, 1, 3, 4, etc. and it goes on until you have all listed where all n tennis balls went. Okay, so you've got all these possibilities in this probability distribution, and what we want to know is we want an event, we want a subset of this. So let's say we want this specific event, so we're going to section off a bit of this event here, which is an event within this probability space. Okay, so this is going to be an event, let's call it the event E, and this event is going to be a subset of this entire probability space, and it's going to be all outcomes where in this great big long list you have little x1 1s, little x2 2s. So basically I need, at some point they can be in whatever order, but I need little x one of these tennis balls to go into 1, and etc. all the way down to I need little xk k's. So basically I need an example of an element that is in here would be you have 1 1 1 1 1, and you have that little x1 times, sorry. Then you have 2 2 2 2 2, and you have that little x2 times, and I'm sorry I'm doing it 5 each time, but then you have 3 3, let's say, and that's little x3 times, and you go on, and then you have k k k, and I can't leave it at 3, k k, and we'll have that little xk times. Okay, so that is an outcome in this event, but there are loads of other outcomes in that event as well, because you do not need to get them in this specific order. You could have them in any possible permutation of this. So what are all the other outcomes in here? They are all the possible different permutations of this, and what I mean by that is here's another permutation. We could have 1 2 1 2 1 2 1. How many do I need to do this right? 1 2 1 2. There we have all of those ones messed up, and then we put all the other ones in the same order that they were originally, k k k k k, and you'll realise that that has exactly the same number of 1s and 2s in as this one up here. Hopefully you have 1 2 3 4 5 1s, so little x1 1s, 1 2 3 4 5 2s, so it's worked. So that is another permutation. That is a different outcome in this probability space, because I was just letting all of these vary from 1 to k and putting absolutely every single one of them into here. So all this will be is in this probability space a different outcome to this. Because we are considering each one of the tennis balls as being a separate little being now, whereas in the original problem we weren't doing that. Okay, so, but however, the probability of this event is the same as the probability that the number of tennis balls that go into basket 1 is little x1, etc. As we go on. So this is a way that we can work it out, basically. Now, what we need to know is how many total events are in here. Firstly, well, that's the total number of permutations there are of this. And you might remember from the combinatorics that the way the number of total permutations of this is basically n factorial, which is effectively the number of permutations of the entire thing, because remember, if you add up x1 plus x2 all the way up to plus xk, that makes little n. So the total number of things we have here is n. So if if we were just asking if they were all distinct things, because all these 1s are obviously the same and all these 2s are the same, but if they were all distinct things, i.e. if we just had a list 1, 2, 3 all the way down to n, and we were asking how many different permutations are there of that, that's the same number of things here, but they're all different now, then that would be n factorial. The problem is that you are overcounting a lot, because all these 1s are just the same, and all these 2s are just the same, and all these 3s are just the same. And the way you take account of that is by dividing through by each one of them factorial. So you divide through by x1 factorial, you divide through by x2 factorial, and you go on and you divide all the way through back to x2k factorial. So you take how many different ways there are of rearranging the 1s amongst themselves, which is x1 factorial, and the 2s amongst themselves. And I want to try and give you some intuition for why that is true. So, okay, so imagine now that in this problem up here, this n different things, imagine I take the first x1 of these and I'm going to demote them. So we have up to x1 different things here. So we have 1, 2, 3 up to x1, and now I'm going to say, I'm going to call you all 1s now. How much does this lessen by? How many permutations do you lose from that, basically? Well, there are absolutely loads of these different absolutely loads of right, okay, let's start from fresh. If we put into a set every possible permutation of the 1 through n things, then we have all permutations. So let's just write one out. 1, 2, 3, all the way up to n is a permutation. Then we would have 2, 1, 3, etc. all the way up to n. That would be a different permutation, just to get some intuition. Okay, now what we are saying is we are taking the first x1 things, and they are now all going to be considered, they're all going to be demoted, they're all going to be turned into 1s. So they're now all the same things. Now basically what we want to know is how many of these permutations does that make equivalent, because it's going to turn loads of them into being the same thing. It's going to turn this one and this one into being the same thing, because all of these terms here are going to be the same term now. So switching those two 1s like that doesn't make any difference. Okay, so basically it's going to split this set up. It's going to partition this set up into equivalence classes of things that are all now, that were in the original probability space, they were considered different permutations, but are now considered the same permutation, because all of these first x1 things are going to be considered the same thing now. They're all going to be demoted to 1s. So we're going to get these equivalence classes of permutations that are now being considered 1. And how many are going to be in there? Well, it's every possible way that you could every possible way that you could permute these these x1 things around. So if you just permute these x1 things, then in their positions, those were all originally counted as separate permutations, but now they're not going to be counted as separate permutations. So in this one there would be x1 factorial different things. Now in these other equivalence classes, what you will have done is you will have done some less trivial maneuvers. So you might, for instance, in here you might have n, 2, 3 all the way up to 1. So you might have swapped the 1 and the n. Now that's not a trivial, that is certainly a permutation in the original probability space where we're considering all n things distinct, but it's still a valid permutation in this new space where I'm demoting these 1, 2, 3 x1 things into all being 1s. Because this is still going to be different even once you've done that. Okay, but there are now going to be absolutely loads of these which are equivalent, which again, so for instance, let me show you, n, 3, 2, all the way up to 1. That's still good. That's going to be equivalent now to this one here, because all I've done is permute these. If this goes up to x1, and here and this one here, all I've done is permute these things that are being demoted onto being the same elements. So again, how many things are there going to be that are going to be equivalent in this equivalence class? Well, it's going to be x1 factorial of them, because it's all the ways that you can permute these x1 things that are all being turned into an equivalent number. And again, each one of these equivalence classes where you have made some non-trivial permutation, but again there are loads of other permutations which are all now equivalent to it because you've demoted these, they'll have x1 factorial elements in, because that's the number of ways of permuting these things amongst themselves. So you maintain the non-trivial difference in the permutation, but you permute these 1, 2, 3 through x1 things. So each of these equivalence classes basically will have x1 factorial permutations in. So the overall number of equivalence classes now, which is the overall number of non-trivial permutations, is therefore n factorial divided by x1 factorial. And we are basically doing this thing, we're doing it k times. So we're demoting all of these things, all of these x1 things to being one thing, all of these x2 things to being one thing, etc. So we're basically just doing a more extreme version of that by dividing through by all of them. Okay, phew, I find that a really difficult concept to get your head around, an even more difficult concept to explain. But if you have understood that, well done, that's the most difficult bit. Okay, so we've got all these events in here, all these outcomes of this experiment of ascribing the n tennis balls which basket they are going into. And we now know that the total number of outcomes in this pink event is given by this formula here. What we now want to know is what is the probability of event E. So we want to know what is the probability of event E, but because this is a nice finite probability space, there are a finite number of outcomes here. There might be a huge number of them because obviously there's k possibilities here, k possibilities here. So the total number of possibilities is k to the little n, but it is a finite number. So we can ascribe a probability to each individual outcome. So this is in fact going to be, the probability of, let's say, the disjoint union of the set containing each individual outcome, which I'll denote S, where S is an element of E. So basically all I said is split this set up into every single little outcome and put these little outcomes in sets by themselves, work out what and basically this event can be broken down into the disjoint union of all of these. Then by the second axiom of probability, this just has to equal the sum over every possible event every possible outcome in the event of the probability of those singletons. So basically I'm saying that the probability of event E is the sum of the probabilities of all of the individual events containing a single outcome for all of the outcomes that are in this event, basically. Okay, so I now need to work out what the probability of one of these outcomes is. But this is the brilliance, that the probability of all the outcomes in here is exactly fixed, and that's why it's going to be so easy, because then we just multiply the probability of 1 by the total number of them, which we've already worked out. And the reason is that the probability of, let's say, this special outcome up here is because each of the trials is going to be independent by hypothesis. We do not, knowing which basket the first tennis ball went into does not affect how likely it is that we throw, doesn't affect how likely it is that we throw the second tennis ball into each of the baskets. So the trials are independent, effectively. The probability that I get this outcome overall is the probability that I firstly throw this tennis ball into the first basket times the probability that I throw this second tennis ball into the first basket times the probability that the third ball goes into the third basket, etc. So the probability that I throw it into the first basket is given by P1. And I'm doing that little x1 times, so I'm going to get p1 to the x1, and I think I should write this down more. I should write some more down rather than writing the answer down. So basically, my argument goes as follows: that the probability of, let's say, an outcome, let's say this outcome 1, 1, 1, 1, x1 times 2, 2, 2, 2, 2, little x 2 times 3, 3, little x 3 times, and then we go on all the way up to k, 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 little x k times. Okay, that's an outcome in a set by itself to make an event, and we want to know what's its probability. But basically, we're saying that this is because each tennis ball is independent. Strictly speaking, what we could do is we could ascribe random variables taking on the value for each, we could ascribe a random variable for each one of the n tennis balls, ascribing the basket that it goes into, and then we could work out the probability of each of them. But we're past that. The probability of this is just going to be the probability of that getting that first ball into the first basket, which is just P1. Then the probability of getting that second ball into the first basket, which is again multiplied by P1. Times P1, and you want that x1 times, then we want to change, we want the next ball to go into the second basket, so the probability of getting that ball into the second basket is P2, and again, we continue that on, we do P2, 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 and we do that x2 times, because we want all of those x2 balls to go into the second basket. We then do P3, P3, and we do that x3 times, and we go on, and we get to PK, and we do that xk times. So basically, we are viewing these trials as being independent. So we're saying the probability of me getting the first and second balls into basket 1 is just P1 times P1. So the overall probability of getting this outcome turns out to be P1 to the power of x1, P2 to the power of x2, because we have x1 P1s, x2 P2s, we have x3 P3s, and then you go on to xk Pks. So we could write this as the Euler product, I is equal to 1 to how far do you go up to k of pi to the power of xi. Okay, so all that says is it's basically this is basically similar notation to the sigma notation, where you write sum from I is equal to 1 to k of, let's say, xi, but instead of adding the terms, you product them. So the first term is P1 to the power of x1, then you times that by the second term, which is P2 to the power of x2, etc., and you go on all the way up to p to the kth term, which is pk, x to the k. So it's just a nice way of writing this great big product here. Okay, so so the next thing to argue is that all of these permutations, every possible permutation of this is going to have the same probability. The reason being that if you take a different permutation, it's still got the same number of x1, it's still got the same number of 1s in, it's still got the same number of 2s in, it's still got the same number of 3s in, and it's still got the same number of k's in. So you've just rearranged them. So the number of p1s, p2s, p3s, pk's you're going to get in this great big product are going to be the same. So the probability of every single outcome in this event E is the same. So this great big sum here effectively becomes this probability. So I'll put that, I'll write it out explicitly. It's P1 to the power of x1, P2 to the power of x2, all the way up to pk to the power of xk. That's the probability of a singleton, and then we just times it by the total number, which is given by this coefficient here, which is n factorial over x1 factorial, x2 factorial, and then you go all the way up to xk factorial. Okay, so a very swish way of writing this is if we write it out again, the probability, I'll write it out, so we can write the probability of the vector x1, x2, all the way up to xk, equaling little x1, little x2, all the way up to little xk. So this is the PMF of the multinomial distribution now, is given by the product, the Euler product, I is equal to 1, in fact actually I should write the n factorial out the front, times the Euler product, I is equal to 1 to k of pi to the power of x to the I divided by xi factorial. So let me just convince you that that's the same thing. This was our original statement here. Now if I work this thing out here, if I expand this, keep the n factorial out the front, then the first term is p1 to the x1 over x1 factorial. The second term is p2 x2 over x2 factorial, so I multiply that by the first term, and I go on, and I get the kth term, pk, x to the k, over xk factorial, and that indeed gives me the same thing as I have there. Okay, so that's a nice, neat way of writing the PMF for the multinomial distribution. Okay, so I just now, finally in this video, the last thing I want to do is just discuss the relation of this to the binomial distribution. So if we make the two possibilities, if we make the vector x just a two-dimensional vector, if we make it x1, x2, okay, and we make the p vector, let's say this p vector, and I should have had a vector symbol over there, the p vector, we just make p1 and p2, but because p1 plus p2 is equal to 1, then we could just write p2 as 1 minus p1, okay? And then basically this PMF becomes the probability that x1, x2 is equal to some little x1, little x2 is equal to n factorial times p1 to the x1, p2 to the x2, but again, because x1 plus x2 must equal the total number of trials, this must equal n, oh, sorry, not x1 plus, sorry, little x1, this should be little x1 plus little x2 must equal n, then I could write little x2 as n minus x1, so I could write this n minus x1, I could in fact put n minus x1 there, n minus x1, where n is the total number of trials, remember, and then we have this divided by x1 factorial times n minus x1 factorial, which is x2 factorial. Okay, and then basically we can combine all this together to get n choose x1, p1 to the power of x1, and then p2, which is just 1 minus p1 to the power of n minus x1, and that's just the PMF for the binomial distribution. So intuitively, the reason it reduces down to the binomial distribution is what we're asking is we have n tennis balls, 2 baskets. So basically we've got n trials, which is the tennis balls, and we have 2 possibilities. So if you called this basket head and this basket tail, and you're just throwing balls into these baskets, and we said this is probability P, this is probability Q, which is just 1 minus P, then it's exactly the same thing. You've just it's exactly the same problem as tossing a coin, where the probability of the coin landing heads is P, and the probability of the coin landing tails is 1 minus P. Okay, so that's why it reduces down to the binomial distribution, and that's all I want to say in this video.